So we're wrapping up section 9.2 here. Just like we saw in the previous video, you could do algebra with power series. You can also do calculus with power series. We can take derivatives and integrals of our power series. Now a series is simply a sum of terms. And we know that we can take a derivative or an integral of a sum by taking the derivative or the integral of each term separately. That result is stated as a theorem here for series. It looks really complicated, but in actual practice it's not nearly as complicated as it looks when you kind of try to write it out. Notice here it says if we start with some power series, this is just a general form for the power series, the derivative, what have they done? All they've done is a power rule, right? They've taken the k power, brought it down in front, and reduced the power by 1. Just the normal power rule for derivatives. It does, interestingly enough, say that notice that the integral of convergence is not changed by the act of taking the derivative. Same thing with integrals. If you integrate, right, integrate our power series, again, notice what they've done. The ck has stayed the same. They've raised the power by 1. Oops, sorry, you can't see that part. And then they've divided by the new power, normal power rule for integrals. And then, of course, we've added that constant of integration. Once again, notice that the interval of convergence is not changed by the act of integration. So let's try a couple of things. And I think we're going to kind of see a few connections here. We'd like to take the derivative of the power series for f of x equals sine x, and then talk about why that result really makes sense. So I know that the series for sine x is, right, if I go back here, I'm just going to take that as my sine x series right from my list. Like so. It does converge for all x, according to our table. What I'm actually going to do here is I'm going to take the derivative on both sides of my equal sign. So I'm kind of going to imagine splitting this up like this. And I'm going to say, let's take the derivative on both sides. Now, of course, the derivative on the left for sine x is cosine x. And then I'm going to take the derivative of my power series on the right. Now I'm taking the derivative with respect to x. So the stuff that just has k's in it isn't going to change. I'm actually going to go ahead and say these are all constant as far as x is concerned. So the negative 1 to the k over 2k plus 1 factorial doesn't change at all. It's just a constant multiplier. And then I'd multiply that by the derivative of the x to the 2k plus 1. Well, that's just a power rule. It's just an exponent. I bring the power down in front, 2k plus 1, and then I reduce the power by 1, so it just becomes x to the 2k. Let's simplify that a little bit. We know that 2k plus 1 factorial would be 2k plus 1 times 2k on down, or in other words, 2k factorial. And that's going to allow me to cancel out those 2k plus 1s. So what I end up with is negative 1 to the k, x to the 2k over 2k factorial. take a look at the series for cosine x. And what you should see is that we have an exact match for what we just came up with. Looks exactly like that. The interval of convergence does not change. Negative infinity to infinity, or in other words, the interval from minus infinity to infinity is I. All right, I'm going to use a similar technique to that to say that sometimes when we take a derivative like this, we might come up with a series that we already knew. But the idea of taking a derivative or even an integral is also a way to come up with new power series for functions that we maybe didn't already have them for. If you take a look at example 7, this time we're being asked to integrate the power series for f of x equals 1 over 1 minus 2x. See what we come up with? And then it says reconcile this result with what you know about this integral in closed form. So I'm actually going to use a blank piece of paper here. In retrospect, I wish I had given us a whole page for each of these two problems. So just so I can set this up the way I want it, I'm going to do that. All right. So for starters, I'm going to write down my power series for 1 over 1 minus 2x. Now what I have on my list is 1 over 1 minus x. So I'm going to have to replace that x with a 2x. And if I replace the x with a 2x here, I have to replace the x with a 2x over here. So it would be now 2x to the k power. Okay. Again, this one said the absolute value of x is less than 1. I'm replacing the x with a 2x. So for me, the absolute value of 2x is less than 1. Notice that that says the absolute value of x is less than a half. So my interval of convergence here is actually going to go from negative a half to positive 1/2. Already know that. All right, we want to integrate this time. So if I integrate both sides, let's start with the integral on the left, and then I'll come back and do the integral on the right. Integrating this, I'd have to make a little bit of a u substitution, right? We'd have u equal 2x. Actually, we want to have the whole denominator. U equals 1 minus 2x. So du is negative 2 dx. And I'd have negative 1/2 du equal to dx. And so my integral becomes the integral of 1 over u, and I replace the dx with a negative 1/2 du. And that's going to give me negative 1/2 times the natural log of u, or negative 1/2 times the natural log of 1 minus 2x, plus c. So good to go. My left-hand side has been integrated. Now in order to keep it equal, I would also have to integrate the right-hand side. So in my series, I can integrate inside the sum. Like so. And once again, I'm going to want to make a u substitution. In this case, let's just go ahead and let u equal the 2x. So du would be 2 dx, and 1/2 du would equal dx. So my integral becomes u to the k, and then the dx is going to get replaced with a 1/2 du.
So I would have, I can pull the 1/2 out of that series. Let me just pull the 1/2 out front.
The integral of u to the k du, normal rules of integration.
We increase the power by 1, and we divide by that new power.
Plus the constant of integration. And then lastly, I could just replace the u with a 2x. Actually, let me just do that right here because I wanted these two things side by side. U is 2x to the k plus 1. All right. Everything's been integrated. We're good to go. But what I'd now like to do is look at these two results. Notice that I could go ahead and I could just go ahead and multiply by 2 to get rid of the 1/2s on both sides here. And if I did that, I would have minus the natural log of 1 minus 2x plus c equals the series, sum from k equals 0 to infinity, of 2x to the k plus 1 divided by k plus 1 plus c. Does that reconcile with something that we know from our list? Let's see here. I'm really looking at this one right here. Get this where you can see it, sorry. Take a look at this. What I have here is almost the same as this, right? Except that the x has been replaced with a 2x. And take a look at what we've got over here. Right? Again, the x has been replaced with a 2x. And the only difference is I have k plus 1s where they have k's. But look at the starting k values. My k's start at 0. Theirs start at 1. So the first one is the first power divided by 1. When my k is 0, that's still a first power and divided by 1. It's really the same. Okay? In fact, if I wanted to, we've talked about this I think once before, I could change that to the sum from 1 to infinity. If I increase k by 1 here, I would have to decrease k by 1 here to compensate. So that would really make this 2x, and then decreasing that by 1 would make that just a k power, and decreasing that by 1 would make that just a k power. And that now is the same as our list. So it checks out. All right, I always like finding connections. We have one more example here, example 8. And again, I really should have given us more space to work on this, so I'm just going to go to a blank sheet of paper. This time we're asked to differentiate the power series for f of x is equal to 1 over 1 minus x. And it says, what function do we now have a power series representation for? So I'm going to start with my function, 1 over 1 minus x. And I'm just going to write it as a power series using my list again. 1 over 1 minus x is the series x to the k. K goes from 0 to infinity. And this converges for the absolute value of x less than 1. All right, let's take the derivative of both sides this time. So the derivative here, this is really 1 minus x to the negative first.
So if I take my derivative, I'd have minus 1 minus x to the negative 2 times the negative 1 for the chain rule, which is going to make that positive again, really 1 over 1 minus x squared. Now in order to keep this equal, I would of course also have to take the derivative on the right. So I've got the sum, and I'm going to leave that blank, k equals something to infinity. I want to talk to you about that in just a moment. I'll use my normal power rule for derivatives, k times x to the k minus 1. And I do want to notice, I do have to change this to a k equals 1 here, because notice if k was 0, that would have been a constant term. And the derivative of a constant term is 0, so the power rule doesn't really start until k equal 1. The k equals 0 term is 0, so I didn't have to bother to write it. Derivative of a constant is 0. All right, so this again is only valid for absolute value of x is less than 1. But what I've got now is a new power series rule that we just figured out, right? This 1 over 1 minus x squared wasn't anywhere on our original list. Nowhere on there was there a power series that looked like 1 over 1 minus x quantity squared. So I now have a rule for that, which I've discovered by using the derivative. The power series for 1 over 1 minus x quantity squared is the series k goes from 1 to infinity of k x to the k minus 1, and it converges for absolute value of x less than 1, or in other words, negative 1 to 1. So using derivatives and integrals of some power series just gives you something you already knew. But sometimes it actually can give you an entirely new power series rule, which is what happened to us there. All right, that brings us to the end of 9.2.